My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 120th International Physics webinar. So good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So hope you are well and safe from Corona pandemic. So as we know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. So we have to start our online programs. I think you have already come to know that our Department of PhysicsPabna, University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 119th international physics webinar, including 2 Nobel laureates speaker. So today I'd like to welcome you all through a joint session between the Department of Physics, Pabna, University of Science and Technology, and the Department of Physics, Massachusetts Institute of Technology, MIT, USA in Physics. And we have with us here today Dr. Phiala Shanahan, Assistant Professor, Department of Physics, MIT, USA, and she has already connected with us. So I'd like to welcome our speaker. So good evening, madam, and good morning to your part. And thanks for accepting our invitation, madam. So
good evening.
We'd like to
very much.
Yeah, I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, madam. So for those who are new, I'd like to introduce that we have divided our webinar into 3 parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver her speech with our student. And at the end, we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar. The title is From Quarks to Nuclei, the Building Blocks of the Universe. And our speaker is Dr. Phiala Shanahan, Madam, Assistant Professor, Department of Physics, MIT, USA. And we can see her academic and career background. Dr. Phiala Shanahan completed her undergraduate degree at the University of Adelaide, Australia in 2011, graduating with a BSc in High Performance Computational Physics with First Class Honors and the University Medal. In 2015, she completed her PhD in Physics also at the University of Adelaide under the guidance of Tony Thomas and Ross Young. She was awarded the Postgraduate University Medal, the South Australian PhD Research Excellent Award, and the Bragg Gold Medal for the best PhD completion in physics in Australia. Throughout her studies, Dr. Shanahan was a member of the American Physical Society and served on the South Australian Branch Committee of the Australian Institute of Physics. Since 2015, Dr. Shanahan has been a postdoctoral research associate at the MIT. Her current research is focused on understanding the gluonic structure of Hadron 11 to the proposed electron-ion collider, and on exploration of nuclear structure using the first principle lattice quantum chromodynamics techniques. Before joining the MIT physics faculty in July 2018, Professor Shanahan was a postdoctoral associate at MIT from 2015 to 2017 and held a joint position as assistant professor at the College of William and Mary and senior staff scientist at the Thomas Jefferson National Accelerator Facility from 2007 to 2018. Professor Shanahan is the recipient of an NSF Career Awards, was named as an Emmy Noether Fellow in 2018 and was listed in the Forbes magazine 30 Under 30 in Science in 2017. Shanahan researches the physics of atomic nuclei, and her works has interesting implication for how we understand dark matter and physics beyond the standard model. Professor Shanahan's research interests are focused around the theoretical nuclear and particle physics. In particular, she works to understand the structure and interaction of hadrons and nuclei from the fundamental quarks and gluon degree of freedom encoded in the standard model of particle physics. Shanahan's recent work has focused in particular on the role of the gluons, the force carrier of the strong interaction described the quantum chromodynamics QCD in hadron and nuclear structure. Using analytic tools and high-performance superconducting computing, she recently achieved the first calculation of the gluon structure of light nuclei, making prediction which will be testable in new experiment proposed at Jefferson National Accelerator Facility and at the planned electron-ion collider. She has also undertaken extensive studies of the role of strange quark in the proton and light nuclei, which sharpen theory prediction for dark matter cross-section in direct detection experiment. To overcome computational limitation in QCD, calculation for hadron, and in particular for nuclear, Professor Shanahan is pursuing a program to integrate modern machine learning techniques in computational nuclear physics studies. So you can see her goals for ID, and see citation more than 1200. So thanks for all of your questions. Now it's time to go to our speaker. So madam, thanks again for accepting our invitation. It's your time, madam. You can start your session.
Okay, thank you very much. It's absolutely a pleasure to be here to talk a little bit about our modern understanding of the structure of the matter that makes up protons, neutrons, and the atomic nuclei in our universe. So the topic of this talk is obviously the structure of matter. And of course, we know that matter is composed of atoms, and atoms have a densely packed nuclear core of protons and neutrons orbited by a cloud of electrons. Our modern understanding is that the structure of matter actually goes one layer deeper, that the protons and neutrons in an atomic nucleus themselves have a substructure. They're made of matter particles called quarks, held bound tightly together by the strong force, manifesting as force-carrying particles known as gluons. And to the best of our current understanding, the quarks and the gluons are it. They are fundamental particles that can't be divided any further. And to the best of our understanding, the structure and interactions, not just of the protons and neutrons, but of atomic nuclei, all the way up to the periodic table and ultimately chemistry, come out of the dynamics of the interacting quarks and gluons. Now, the quarks and the gluons and their interactions are encoded in what's known as the standard model of elementary particles. It's shown here. And this framework, which was put together in the 1970s, has just 17 fundamental particles, shown here, and it describes 3 of the 4 fundamental forces, notably excluding gravity, in a very elegant and beautiful and very predictive framework. So here we have matter particles called quarks, which come in different types or flavors. We have the electron and the electron neutrino and its heavier cousins. We have force carriers of the 3 forces included in the standard model. We have the photon, the force carrier of electromagnetism, the W and Z bosons, which are the force carriers of the weak force, and the gluon, which is the force carrier of the strong force. And finally, we have the Higgs boson. And so this framework, it is so predictive that in fact, a number of these particles were predicted because they exist in the theory before they were seen experimentally. So most recently, there were the W and Z bosons in 1983, the top quark in 1995, and then a lot of us might remember the Higgs boson in 2012 was the last remaining component of the Standard Model that was found by experiment at the Large Hadron Collider. So this is an extraordinarily successful description of the matter in our universe that has withstood almost every experimental test. So to give you just a small example, so the magnetic moment of the electron, that's how much torque an electron feels in a magnetic field. This is the most accurately verified prediction in the history of physics. So what I'm showing here is actually the anomalous magnetic moment, so the deviation of this from the tree level result or from the classical result, that's the A here. And what you see here is agreement between theory and experiment to 12 significant figures. So for any students in the audience who are studying quantum field theory, you have an idea when I say what a heroic effort this comparison is. It took 30 years of effort. There are 12,000 Feynman diagrams up to 5 loops to make this comparison, and theory matches experiment to 12 significant figures. And it's not just at single static quantities where the standard model predicts what we see in experiment. Here's just one more example. If we take deep inelastic scattering of the electron on the proton, so you take a proton and you hit it with an electron so hard the proton breaks apart. That scattering is described by functions known as structure functions, shown here. And in this chart, you see those structure functions shown here on the vertical axis and the energy scale on the horizontal axis over 5 different orders of magnitude. And you can see that the theory predictions in yellow compared to the experimental results, the colored points, agree across all 5 orders of magnitude of energy scales. So the standard model is beautifully predictive and successful. However, we also know that this beautifully predictive and successful theory doesn't describe everything. So just one example that we'll come back to during the talk is dark matter. So despite the successes of the standard model, we also know that it describes only this sliver, this 5% of the universe pi, where the pi shows the energy distribution in the universe. And really, most of the energy distribution is dark energy, but even 5 times as much as the sliver of normal matter described by the standard model is dark matter, which is not described by the standard model. So we have a beautiful, symmetric, predictive theory, but we know that it is not complete. So just one example was that dark matter and dark energy are not included, but there are others. Neutrinos have masses in nature, they don't in the standard model. There's an asymmetry between matter and antimatter in the universe, that galaxies and so on are all dominated by matter, not antimatter. Why? The mechanism isn't explained in the standard model. Of course, gravity is not included, and so on. So, of course, one of the primary missions in physics is to understand in what way our best current theory of nature falls short of describing what we observe about the universe. And just one way we look for so-called new physics, so physics beyond the standard model, is at what we call the intensity frontier. So these are experiments where we're looking to probe the rarest standard model interactions and see a deviation from what we predict, and look for evidence of beyond standard model physics. So these sorts of intensity frontier experiments include experiments looking directly for dark matter. It includes neutrino physics experiments, other experiments listed here. And what all of these have in common is that they use nuclear targets. And by that, I mean they use targets for the experiment which are made of nuclei. And so to be able to see deviations from our standard model predictions and find new evidence for physics beyond the standard model, we need to understand the standard model physics of the protons and nuclei in those targets, in those experiments. So this sort of long-winded introduction was to describe that the mission of understanding the quark and gluon structure of matter is important in several ways. So firstly, for its own reason, to understand the emergence of complex structure in nature. How do we get all of the complexities of nuclear physics out of this beautifully predictive, symmetric, in some ways simple theory of the standard model? But secondly, we also need it to be able to set backgrounds and benchmarks in searches for new physics beyond what we understand from the standard model of particle physics. So after a little bit more introduction, this is also the structure of the talk. So I'll give some examples of how our understanding of the quark and gluon structure of matter can contribute to these efforts here. And then finally, we'll come back to how advances in computing and algorithms feed back into improving our understanding of the quark and gluon structure of matter as well. Okay, so to talk about the structure of matter is to talk about the strong force, which is described by part of the standard model known as quantum chromodynamics, or QCD. So the theory of QCD describes the strongest of the 4 forces in nature. That's the force that's binding quarks and gluons into protons and neutrons and other subatomic particles. It's binding protons and neutrons into nuclei. It's also responsible for forming other types of exotic matter like the quark-gluon plasma. So clearly, the strong force is important if we're talking about the structure of a proton or a nucleus. In the strong force also, however, we have some challenges. So in particular, the interaction strength of the strong force depends on the energy scale. So that's what I'm showing here in this figure. So this is the coupling, the interaction strength of the force. And on the horizontal axis, we have the energy scale. So you see that at large energy scales, the coupling is small. And at low energy scales, it becomes large. Now, at large energy scales, when you have a small coupling, what that means is that you can do what's called perturbation theory. That means that if the coupling is a small number, if you square that small number, it becomes even smaller. If you cube it, it becomes smaller again. So you can expand in powers of that coupling. And you know that the higher order terms become less and less important as you expand. It's a perturbative expansion. At low energies, however, which is what's relevant to the structure of, say, the proton at rest or a nucleus at rest, the coupling is large, and so you can't do this sort of a perturbative expansion. The second order, the squared term and the cubed term are actually more important, not less important. And so you can't expand in powers of the coupling and then stop at some point and have a good prediction. What this means is that studying the strong interactions, studying the theory of QCD is challenging. And the only way we know how to do it in a systematically improvable way is via a numerical method known as Lattice QCD. It's called Lattice QCD simply because you're studying the theory of QCD, the theory of the strong interactions, on a four-dimensional lattice or grid of space-time points. So you make space-time into a grid or a lattice, and then computing, so calculating something from the equations of QCD just looks like integrals over the values of quark and gluon fields on each site or each link of this lattice. So essentially, calculations in QCD become very high-dimensional integrals in something like 10 to the 12 variables. And the way these integrals are done is via what's called importance sampling. And so just for some intuition on this, you can think just about quantum mechanics, where we know that while all paths contribute, paths near the classical path dominate and the others are less important. So in the context of our QCD integrals, you compute physics on a set of samples of the quark and gluon fields, and you know that some of those sets are more important than others of those sets, so you can sample them correspondingly more. And this allows you to do such a very high-dimensional integral in a very efficient way. So this is the most technical slide I'll show, really. Let me step through what this is saying. This is putting the same thing I said on the last slide in just a little bit more technical detail. So the equations of QCD, we study them in a Euclidean space-time on a lattice or a grid. So of course, if you put space-time onto a grid, it means that you have some non-zero spacing between the sites of your grid and some finite volume. So of course, to recover continuum QCD, you have to take the limit as the spacing becomes small and the volume becomes large. In a numerical calculation, you can do things that aren't possible in nature. For example, you can use heavier quark masses than there are in nature, and actually that makes the calculations cheaper. So it's a convenient computational tool. And then here is explicitly what it looks like to compute the expectation value of observables, so compute a value that you might want to compare to an experimental measurement in QCD. So let me step through what this equation is saying. It will be familiar to you if you've studied quantum field theory, which is the framework that describes theories like QCD. What this is saying is we have an integral over the quark and the gluon fields here. So we're integrating over all possible values of those fields. O is the operator, the observable that we'd like to measure. And this integral is weighted by the exponential of the action, where the action is the function that describes the quark and gluon dynamics in QCD. And so this importance sampling approach that I described before, if you sample these fields with this exponential of the action already built in, then computing this integral just becomes taking the average of measurements over the samples, because this factor is already built in. Okay, and so this is essentially how these calculations progress. And some of the challenges in this sampling here are what we'll come back to at the end of the talk when we talk about how advances in algorithms can improve our understanding of the structure of matter. So just a few things to emphasize about this approach. So the first is that the input to Lattice QCD, so this numerical tool to study the equations of QCD, the strong interaction, has the same free parameters as QCD itself. That is the quark masses and the strong coupling. So once you've fixed those parameters by matching to some number of experimentally measured quantities, like the measured hadron masses and one additional experimental input to fix that lattice spacing, or equivalently the strong coupling, then everything else you calculate in this framework, all the way up to the structure of nuclei, are predictions from the theory. I also want to emphasize that the calculations are extremely computationally demanding. So we use the world's largest supercomputers many millions of CPU or GPU hours. So just to give some context, some of the calculations that I'll show would have taken about 30,000 years on my laptop computer. This is Summit, so currently one of the world's largest supercomputers. And what Summit can do is if every person on the Earth did one arithmetic operation every second for a year, that's about what Summit can do in 1 second. So we're really pushing the boundaries of supercomputing with these calculations. I should also say that this numerical tool, even though it's extremely computationally demanding and complex, it actually works. So just a couple of examples of that. The ground state hadron spectrum. So that means the masses of things like the proton have been reproduced. Even the proton-neutron mass difference has been reproduced in numerical calculations, including both the strong and electromagnetic interactions. So that's what's shown here in this figure. These are the mass differences between the proton and neutron here and between other pairs of particles like the proton and neutron, what we call members of baryon isospin multiplets. And what you can see is that the computed values match experiment, and some of them are even more precise than the experimental values. There have also been predictions for new states with controlled uncertainties. So in this figure here, every one of these points is the mass, the energy of a state. In these case, states like the proton and neutron, but with a heavy quark. And what you see here, the red lines are the experimentally measured states, and they all agree with the calculations. And this one here, in fact, that red line, I put that on in Photoshop. That was a prediction from the numerical calculation. And then the LHCb experiment at the Large Hadron Collider went and they found that state exactly where it was predicted to be. So this numerical tool is precise and controllable and making verifiable predictions from our theory about the universe that we can then go and test. And so we'll see many more examples of this through this talk, but theory here is really complementary to experiment in a very deep way. Okay, so let's come to some specific examples of how we can understand more about the complex structure of nature from theory calculations of QCD, the theory of the strong interactions that describes the dynamics of quarks and gluons. So I also want to emphasize that I'll be discussing this mostly from a theory perspective, but as I just mentioned, there's a great synergy between experiment and theory that we'll see some more examples of. But this goal of understanding the quark and gluon structure of matter is also a defining issue for experiments. So there's experiments all around the world also seeking to measure the sorts of quantities I'm talking about, studying from the theoretical perspective. Okay, so one class of questions that's particularly topical right now is the gluon structure of, say, the nucleon, which is the proton or neutron. And the reason this is particularly interesting is that we know that, say, protons and neutrons, so nucleons, are made of quarks and gluon, quarks really bound together by gluons, which are the force carriers of the strong force. And over the last 60 or so years, we've been able to achieve through experiments a fairly detailed picture of the quark structure, the distribution of quarks inside a proton. But we do know that gluons are important in nucleon structure, but we've been able to measure far less about the details of the gluon structure of the proton, essentially because the gluon doesn't couple to an electromagnetic probe. So the ways that we use experimentally to measure the quark structure of a proton can't be used to measure the gluon structure of the proton. So one thing that we have been able to measure is what I'm showing here, the parton distribution functions in the proton. So what that is, it's the number density of partons, so that's quarks or gluons of some type or flavor F, carrying a fraction x of the longitudinal momentum of that proton. So that longitudinal momentum fraction x here is on the horizontal axis. And these lines here correspond to different partons, different types of quarks, or the gluon. So this is up, down quarks, C quarks, so that's strange quarks. And here's the gluon. And we do see that the gluon parton distribution function is really dominant at low longitudinal momentum fraction. But in comparison to what we've learned about the quark structure, there are still fundamental qualitative questions about the gluon structure of the proton that we don't have any answers to at all. So the sorts of questions that I mean are things like, how much do gluons contribute to the momentum, the mass, the spin of the proton, to something called the D term that we'll see later? What about the three-dimensional distributions of gluons in a proton? So these are encoded in things like gluon distribution functions, quantities known as form factors, the pressure distribution inside a proton. And then, well, what about nuclei? How does the gluon structure of a nucleus look different from the gluon structure of protons and neutrons? And that's described by things like EMC effects or exotic glue. So we do have answers to some of these questions, and others are still as yet explored. So we can look at a couple of highlights from the last few years. So a highlight from last year was that in one of these numerical lattice QCD calculations, all terms of the momentum decomposition of the proton were calculated. So that means here in this chart, you're seeing that up-type quarks contribute about 36% to the momentum of the proton. Down quarks, about 19%, strange quarks, about 5%, charm quarks, even less, and gluons contribute about 43% to the momentum of the proton. And all of these parts were computed separately in a calculation with fully controlled systematic uncertainties, each contribution individually computed, and they all add up to 100%, as of course they should, that between them, all of the quarks and gluons carry all of the momentum in the proton. So there's been great success in the last few years, really understanding the role of the different quarks and the gluons especially in the structure of the proton. And another example, we can go to also away from these sort of simple static quantities to more complicated questions like the pressure in the proton. So we know that the quarks are confined inside the proton. So if there's some sort of expanding force inside the proton, there also must be a compressive force to cancel it, since the proton is stable. So if we make a cartoon of the pressure distribution in the proton, and so here on the horizontal axis, you can think about moving out from the center of the proton. So this is the center of the proton here, and here we're moving out along a radial distance from the proton. And what I'm showing here on the vertical axis is that radial distance squared times the pressure. I'm showing this because this is the quantity that has to integrate to 0 for stability. Then we can make a cartoon of the proton's pressure. If you have a peak that is a repulsive pressure, then it must be cancelled by a trough here, a confining pressure for the stability of the proton. And if we look at this cartoon, we can ask qualitative and quantitative questions about it. We can say, well, what is the peak? What's the maximal pressure inside the proton? Is it more like a bike tire that's 10 to the 5 Pascal, or more like the ocean floor at 10 to the 8 Pascal, or more like a neutron star at 10 to the 34 Pascal? What's really the pressure inside the proton? How do quarks and gluons contribute? And do they contribute in different ways to this pressure distribution? What's the radial extent? How far out does the pressure distribution inside the proton go? So these are questions that we're just beginning to be able to answer. So a couple of years ago, there was a first experimental extraction of the pressure distribution in the proton, which was quite remarkable, found some very exciting things. The first is that the peak pressure near the center of the proton is something like 10 to the 35 Pascal, which is greater than the pressure estimated for neutron stars, which are the densest known objects in the universe. What was also true of that experiment, however, is that the experiment is only sensitive to quark contributions, not to gluons. So to get a complete picture of the pressure in the proton, what we were able to do is combine the new experimental results measuring the quark contributions to the pressure with first numerical calculations from theory of the gluon contributions to the pressure. And so by combining experiment with the numerical approach to QCD, we're able to put them together and have a first complete picture of the pressure inside the proton. And that's shown in this cartoon here. So this is the same cartoon that we saw before, but now with numbers on the axis. And the blue here, the dark blue, is what you get if you ignore the gluons, or you assume that gluons just contribute in the same way as the quarks. And what you see in red here is what you get if you include gluons explicitly calculated using Lattice QCD. And you see that the peak shifts a little bit, but also qualitatively, there's this very clear feature that the gluons extend the region over which the pressure is non-zero, and they're clearly important in the pressure distribution in the proton. So then we can ask the question, well, what about not just the proton? Can we compare these sorts of quantities, like the momentum distribution, like the pressure distribution, between different types of states, different types of particles, and can we learn something about them in that way? So we can look from the nucleon to the proton and neutron, and we can compare that to the pressure distributions in, say, the pion. So the pion, which is a very light hadron state in nature. Now, this is particularly interesting since both the pion and the nucleon, if we look at just the momentum carried by different types of quarks and by the gluons, the quark and gluon momentum fractions in the nucleon are about 50% each, and they're also about 50% each in the pion, so very similar. But if we look away from that simple static quantity to actually the pressure distribution, we see significant differences here. So the pion pressure distribution is much narrower. It has a much higher peak. And so we really see qualitative differences here. We also see differences in the roles of quarks and gluons between the proton and the pion, in which region quarks are dominant versus gluon. So we can learn a lot more about the differences in structure between the hadron. So a natural question is then to say, well, if we can look at the proton and neutron, the nucleon, we can look at the pion. What about light nuclei? And by studying the pressure distribution of light nuclei, we might be able to get insights into the equations of states of neutron stars as well. And so that's work in progress. And studying light nuclei from this numerical tool of Lattice QCD is actually an extremely hard problem computationally. So to give you just a sense for how and why this gets hard, we're doing a numerical tool which involves sampling, right? And the noise, the statistical uncertainty in that sampling grows exponentially with the atomic number of the nucleus you're studying, so exponentially with the number of nucleons. On top of that, the cost of doing the calculation on each sample grows factorially. So we have a compounding exponential and factorial cost that's growing as we try to study nuclei in this framework. So extremely computationally demanding. The calculations of the proton are already using the largest supercomputers in the world, and now we have exponentially more expensive calculations. So although this is so expensive, calculations have begun. So the very first calculation was in 2013, and so far almost all calculations have been with unphysical values of the quark masses, where the quarks are heavier than they are in nature, just to reduce the computational cost as we learn how to do these calculations. So a number of groups around the world have been doing these sorts of studies. Here are some recent highlights. The collaboration that I'm part of is the NPL QCD collaboration, the nuclear physics from Lattice QCD calculation. And I'll talk about just a couple of examples of some recent work. So one example is a key question if we want to know about the quark and gluon structure of nuclei is, how is the quark and gluon structure of a nucleus different from that of protons and neutrons stuck together? So these sorts of differences are encoded in what's known as EMC type effects. It's named after the European muon collaborator that first observed these sorts of effects in 1983. And so what this figure here is showing is the deep and elastic scattering. So that's when we probe the structure of nuclei by scattering electrons or muons or neutrinos off the nucleus. The deep and elastic scattering cross-section ratio per nucleon for iron to deuterium versus the longitudinal momentum fraction that we saw before on the horizontal axis here. And what you see here is that this thing here is clearly not 1. And what that means is that deep and elastic scattering off a nucleus is not the same as deep and elastic scattering off the collection of free protons and neutrons that would make up that nucleus. This is nuclear effects inside a nucleus. So these are the sorts of effects that we'd like to understand from our understanding of the standard model of particle physics, from our understanding of the strong interactions, the theory of QCD. And just the simplest thing we can look at is nuclear effects in the breakdown of momentum carried by the quarks in the nucleus. So we saw before the momentum decrease.
Dear viewers and students, so we are very sorry to inform you that we have disconnected with our speaker. We are trying to reconnect with our speaker, so please stay with us. Hello. Hi, madam, can you hear me?
I can hear you.
Okay, we can hear you.
So
yeah,
I'm not
okay.
Cut out.
Yeah, maybe from here.
From here?
From momentum fraction.
Oh, okay, very good. I'm sorry about that.
It's
So,
okay.
so I wanted to say that the simplest thing we can look at is how the momentum carried by different types of quarks in a nucleus differs from that carried by different types of quarks in the proton. So the figure that I showed just a few slides ago. And so what I'm showing here is the ratio of that, how much momentum is carried by the combination of up minus down and the combination of up plus down quarks in helium to that in the proton. And what you see here in this figure, the red band is the results of a calculation using Lattice QCD. The blue ellipse was an experimental constraint from global fits to experimental data from lepton nucleus scattering. So that's scattering of particles like the electron on nuclei. And what you see is that by combining the Lattice QCD theory calculation with the experimental constraint in pale blue, we go to the purple constraint here. So combining experiment and theory together gives us a better constraint on the quark and gluon distributions in nuclei, and in particular, the nuclear effects in those distributions. Okay, so studying nuclei from the standard model, as I mentioned earlier in the talk, also gives us a way of having backgrounds and benchmarks for searches for new physics beyond the standard model. So I'll give just one example here, come back to an example that we had earlier in the talk, is that there is really compelling evidence for dark matter. So from this figure here shows a picture of the Coma cluster, which is a large cluster of galaxies near Earth, and it was observed as far back as the 1930s that the gravitational attraction required to hold that cluster together is more than what's provided by the mass you can infer from the luminous matter, the stars that you can see. So it's like there's something else interacting gravitationally to hold this cluster together. There are famous pictures like this one. This is a false color image of the bullet cluster, where what you see in purple is the mass that you can infer gravitationally through gravitational lensing. So that's matter that you know is there. And the pink is matter that you can see from luminous matter from say, stars. And what you see is this very clear separation. And we understand that is happening from when two galaxies collide and all of the normal matter, the luminous matter, collides and stays in the center while the dark matter continues on. And you get the separation like this, which has now been observed in many other examples, but this is just one of the most famous ones, which gives you further evidence for dark matter. There's evidence from galactic rotation curves, from structure formation, from the cosmic microwave background. So we have compelling evidence that dark matter, in fact, is something like 26% of the energy density pi of the universe, and that the normal matter described by the standard model is only this very small sliver of about 5%. Of course, an even bigger fraction of the pie is something I won't talk about today. It's dark energy. It's whatever is responsible for the accelerating expansion of the universe. But if we focus on this dark matter part of the pie, it's matter that we don't understand. It doesn't emit or absorb light. That's why it's dark. It does interact through gravity. That's how we know it's there. So there are very many models for dark matter. And just to give an idea of that, I like to show this figure from Tim Tate. And what you see here is sort of a Venn diagram of lots of different types of models of dark matter. There's supersymmetric models, there's models with axion-like particles, there's extra Higgs, there's extra dimensions over here, there's dark photons, there's hidden sector dark matter, technebaryon, so all sorts of different models for dark matter. And of course, what we need to do to learn more about dark matter is constrain the space of models through experiments. So just one class of experiments where we look to find dark matter through its interactions here on Earth is through what are called direct detection experiments. So essentially, the idea is that we build a very large detector deep underground to shield it, and we wait. We wait for dark matter to hit the detector. And so a class of dark matter particles that we would be able to detect in this way are called WIMPs. That's weakly interacting massive particles. This means they interact through the weak force. And of course, if we have a detector, the detection rate depends on the properties of dark matter, which is what we'd like to know. And it also depends on the probability for an interaction with the nucleus. So the figures, so the limits on the probability for the interaction with the nucleus, so what we'll call the WIMP nucleon, so this is our weakly interacting massive particle with a nucleon, that's a proton or neutron, from direct detection experiments, look a little bit like this. So this is the spin-independent WIMP nucleon cross-section on this axis, and this is the mass of our weakly interacting massive particle on the horizontal axis. And each line here comes from a different experiment. And the way this works is that the phase space above these lines is ruled out by experiments, and below the lines is where possibilities for dark matter still exist. So what you'll notice about this figure is that this is putting a limit on the interaction probability for the dark matter particle with the nucleon, which is a single proton or neutron. But the experiments are intensity frontier experiments, as I described earlier in the talk. The detectors are made of nuclei, not protons or neutrons. So for example, the xenon experiment here is made with xenon nuclei in the detector. Those are very large nuclei with 130, 140 protons and neutrons. So in going from the experiment, which measures the interaction of dark matter or doesn't see the interaction of dark matter with xenon, and thus puts a limit on it, to this, which is the interaction cross-section with a proton or neutron, there's been a translation that's happened here. So the simplest translation you can do is you can say, well, dark matter interacts with just a single proton or neutron in a nucleus. And so then the cross-section interaction probability with a nucleus is just scaled by the atomic number A, so the number of protons and neutrons, with the interaction probability of your dark matter candidate with just a single proton or neutron N. And this we can calculate very precisely in Lattice QCD. This is the Born approximation. However, well, what if dark matter interacts with multiple protons and neutrons in a nucleus at once? So it's not just the Born approximation. You're not just multiplying by A, but there's terms like this, where your dark matter candidate is interacting with multiple protons and neutrons. Though we can't do this rescaling because this second term is not known. And if it's significant, it could really change the limits we put on the properties of dark matter from our experiments, which look for dark matter scattering off large nuclei. So this is something that we've been able to get insight into from direct lattice QCD calculations. So the spin-independent scattering of these sorts of candidates is governed by what's called scalar matrix elements. Although we don't know the theory of WIMPs, the microscopic theory, just the low energy limit of any generic spin-independent interaction is scalar. So that's the relevant interaction to study here. And lattice QCD calculations with larger than physical pion masses show significant nuclear effects in helium-3, which is the largest nucleus that we're able to study directly. So what this figure here shows you is a deviation from that naive scaling. And each different color here is a different light nucleus, the deuteron, the diproton, and helium-3. And each column here is different combinations of quarks. And what you see here, this red line and these green points here, these are over 10%. That means we have over 10% deviation from our sort of naive scaling just in helium-3. And then the experiments actually use that has 3 protons and neutrons. And then the experiments use, for example, xenon with a very large number of protons and neutrons. And we want to say that there are no significant nuclear effects in order to place these limits. So although this experiment is not, this calculation is not in the xenon, and it has some systematics that are not controlled, essentially what we were able to say is that there are unexpectedly large multi-body effects that you can't neglect in the interpretation of dark matter direct detection experiments. And so there's more work needed on this front. There's a calculation of the physical quark masses, so with controlled systematic uncertainties in progress, and that will really be able to contribute to our interpretation of what not seeing dark matter scatter from xenon or seeing dark matter scatter from xenon means about the properties of that dark matter and the interactions of that dark matter with protons and neutrons. So theory sort of plays a key role in connecting between experiment and the implications of experiment here. So, of course, I mentioned that we want to understand dark matter scattering on xenon. So that's atomic number A equals 131. And our calculations were in helium-3. So that's atomic number A equals 3. And so there's clearly a very large gap there. So how do we get from the nuclei we can study numerically to the larger nuclei that may be phenomenologically relevant? So one way is through nuclear effective theory. And so that is that the one-body pieces are dominant. The two-body pieces are subleading but non-negligible. So of course I said that 10% was an unexpectedly large effect, so that it's still just 10%. So there is a hierarchy in terms of these interactions. So we can think about determining the one-body contributions from lattice studies of single nucleons, the two-body contributions from lattice studies of A equals 2 nuclei, and so on. And then match effective theory and many-body methods to the lattice calculations to make predictions for larger nuclei. And so the sorts of problems we'd like to study, so just some examples of intensity frontier experiments where this is very relevant. One is scalar matrix elements in A equals 131 for xenon for the dark matter search. I didn't talk about these, but you want axial form factors of argon, that's A equals 40 for some neutrino experiments. The Dune long baseline neutrino experiment is a new experiment being constructed in the United States to measure the properties of neutrinos. You can look for double beta decay rates of calcium. That double beta decay would tell us whether the neutrino is its own antiparticle or not, if we see a particular type of decay called neutrino-less double beta decay. And if we could make predictions for that process in the lightest nucleus that can undergo that decay, that's calcium, that would be very valuable. And so all of these types of questions are where we'd like to be able to do direct calculations in larger nuclei. So as I mentioned earlier, these are exponentially harder problems. So if we want to do them directly, we're going to need exponentially improved algorithms. So just for the last few minutes, I'll come to just a hint of how advances in computing and algorithms can feed back and improve our ability to study the structure of matter from first principles. So this is really just a hint, but you saw earlier that in doing these sorts of lattice QCD calculations, a key step is that we need to generate these samples, these configurations, these samples of the background quark and gluon fields with a known probability distribution given by the exponential of the action, where the action is the function encoding the quark and gluon dynamics of the theory. The way we normally do this generation is through a process known as Hamiltonian or hybrid Monte Carlo, but you can just think of it as being an updating process. You go from one sample to another in a chain through, it's a Hamiltonian dynamics coupled with a Markov chain Monte Carlo process. Now, this sort of a chain-based updating method is one of the most efficient ways we know to explore this very high-dimensional space. But also, since you're making small updates from one to the next, you have some correlations between the steps in your chain. And what you really would like is uncorrelated samples. And so you need to take samples, every n steps in your chain for them to be uncorrelated. Now, a particular problem with this is that these updates are close to local or diffusive. And so what that means is that they essentially move out from a site like this. And so what that means is that as the lattice spacing becomes small, which is of course a limit we have to take to return to continuum physics, the number of updates you need to change physics on that fixed physical length scale diverges and becomes large. So if you have a coarse lattice, maybe you only need a few updates to change physics on a fixed scale that's relevant, say the size of the proton. And if you have a fine spacing, you need very many updates. So this is a manifestation of critical slowing down in this context. It means that it becomes more and more expensive to generate decorrelated samples as the spacing becomes small, which is a limit that we have to take. So how can we solve this with new algorithms? So just to give you, again, a framing of the problem, we want to generate these configurations with a known probability distribution. So if we take a toy theory where we have just two-dimensional samples, it means that we want to generate samples like this with these specific log probabilities, and samples like this, which is just random noise, much less often. So we want to sample these images in a very specific way. So this clearly has parallels with the image generation problem that's seen a lot of attention in the machine learning community. So in the machine learning community, there's been great success generating pictures like this. So these are not photos of people, these are fake pictures of faces generated through AI. And so if you can train a machine learning algorithm to generate pictures like this and not this, maybe you can train the same sort of algorithm to generate pictures like this and not this, which is essentially the problem we have in our sampling. So there are a few very key differences, which we'll see, but some of the basic ideas can be transferred. So one way of being able to do this sort of a generative approach is through what are called flow models. And the idea is very simple. The idea of a flow model is that if you can optimize or train a function to give you a change of variables, and that change of variables takes you from an easy to sample distribution to the distribution you actually want, then you're done. Then sampling's easy. You just take samples from the easy to sample distribution, you put them through your function, and out come samples of the hard distribution that you're trying to sample. And this is essentially what a flow model is. It's using machine learning tools to optimize this function that takes you from an easy to sample distribution to the complicated one you're interested in. If you can do this in such a way that that function has an invertible and tractable Jacobian, then you can even make this sampling exact through a Metropolis Hastings accepted step. You can make this sort of a function extremely complicated by composing many simple layers together, which can mean that it can be very expressive and describe a very complicated transformation from an easy distribution to a hard distribution. So unfortunately, we can't just use the same sort of functions that were used to generate images because we have some specific challenges in applying these sorts of tools to QCD, to the strong interactions. And so one of those in particular is that we have very specific symmetries in our samples of gauge fields. We have rotations and translations in 4 dimensions with specific boundary conditions. So this field configuration on this field configuration encode the same physics. They're identical from a physics perspective, but clearly they don't look very identical. So we have to encode that in the network somehow. And there are even more complicated transformations. There's something known as a gauge transformation, where you think about each link on this lattice being represented by a matrix, and a coupled transformation of all of the links in a different way by this specific transformation property here. It's called a gauge transformation. Means that these two configurations actually encode the same physics and are also identical. So of course, images don't have symmetries like this at all. And so if we just compare the statistics or some of the details of an ensemble of lattice gauge fields and a benchmark image set for machine learning, we'll see some significant differences. So the first is the symmetries, but we also have other differences. So for example, each gauge field is represented by something like 10 to the 9 numbers, and we want, say, 1,000 samples. That's a very opposite data hierarchy towards the images, where they might be described by 3,000 numbers each, and you have 60,000 samples. So we have far more degrees of freedom per sample than number of samples. So any sort of training approach where you need training data won't work for us. It's the collection of gauge fields that has meaning, whereas each image on its own has meaning. So in our case, we want the random noise very rarely, but we do want it with a very specific probability that's just very low. Whereas if you're generating pictures of faces, you never want the picture that's just random noise. Long distance correlations are important in our gauge field, whereas it's local structures in the image. So like an eye and a nose are local structures with meaning of their own. So there are significant differences, which means we need to really redesign some of these machine learning algorithms from the ground up. And so this is something we've been able to do. I won't tell you any of the details other than to say that we've been able to incorporate symmetries into our theories. So for example, on each link here, I said you have a matrix, a 3x3 complex matrix with unit determinant, and then trying to incorporate the symmetries, you hit all sorts of challenges. The first is that a matrix, of course, it's a group valued object. And so you're not just living on the real line, but on a compact connected manifold. So you have to design these sorts of transformations for compact connected manifolds with all of these specific symmetries. And so here's just a cartoon of the sort of machine learning architectures we've designed that incorporate symmetries on these group valued manifolds to update from one layer to the next. And with these sorts of machine learning architectures, we've been able to see some successes in sampling for field theories. So here's an example for a simple field theory, a U1 field theory. Just for context, QCD is an SU3 field theory built on a different group. This is a simpler case. And what we find is that this critical slowing down in sampling is significantly reduced. I'm showing that in this figure here, which shows a sampling of a quantity known as the topological charge, which is a winding number for the gauge field. And what you see here is that conventional sampling algorithms in the blue here and in the gray, as we go along, this is the step in your sampling, they're very stuck. They're updating very, very slowly. You see that they're flat for long periods of time. But our machine learned sampler in orange is sampling very, very efficiently. And what this translates to in cost is a significantly reduced cost per independent sample using the machine learning algorithm. So this is a measure of the cost. And you see here conventional sampling approaches in blue and in black diverge exponentially as we move along this critical line here on the horizontal axis, whereas the machine learning model here in orange stays reasonably flat, and you have orders of magnitude more efficient sampling for the machine learning model versus conventional sampling approaches. So this is just a sort of a teaser, a hint of some first successes, a proof of principle of an efficient, exact machine learning algorithm for lattice field theory. We've already extended to the case relevant to QCD, but there's significant work needed to scale this all the way up to the scale of state-of-the-art calculations, which run on the largest supercomputers in the world. So although we still have to scale to apply this to the sorts of physics problems that I motivated earlier in the talk, there are lots of interesting interdisciplinary applications. It turns out if you think about a robot arm with many joints, on each joint, the position of that joint is described by angles, which live on compact manifolds. So there are applications of the algorithms we've designed also to robotics, to similar approaches have been used in molecular genetics and drug design. So there's lots of interdisciplinary application to this sort of advance. So then finally, just to summarize, we sort of had a broad look at understanding nuclear physics from the standard model. And so the first part of the talk was really how first principles calculation of QCD, that's the strong interaction part of the standard model, can reveal the structure of protons and neutrons and nuclei, and also give us benchmarks for searches for beyond standard model physics. And then we talked a bit about how new algorithms, especially in machine learning, can help us reach beyond what are the current frontiers of this field. Thank you.
Thank you, madam, for your wonderful presentation. So we have got a few questions and a guest with us. So I'd like to welcome our guest, Dr. Nur Abdullah sir. Sir, welcome to our International Physics webinars. Thanks for joining with us, sir.
Thank you.
So if you have any question and any comment, you can ask.
Thank you, Dr. Pretam. Thank you, Phiala, Shanahan. This is indeed a great lecture, and many things I have learned from your lectures. The first of all, I would like to say, basically, the pronunciation of Western people are not well understood to us. But one thing I should say, your each and every word is very well understood to us.
Oh, very good. Thank you.
You know, we are not very much familiar with QCD, Lattice QCD. I think most of us do not well understand the Lattice QCD, quantum chromodynamics, etc. But the way you have given the lectures, fantastic, really fantastic.
Oh, very good. Thank you.
You have started from the basic. You started from the what to say, the basic of QCD, basic numerical structure, and explain the recent development in this field. I have just one question. You have shown that for pion distribution, for pressure distribution of pion, the peak value has higher value than that for proton. Does it mean that inside a pion, the pressure is higher than inside a proton?
That's right.
Yeah. Oh, thank you.
Yes.
Thank you. Okay.
Yeah, no
thank you very much, and thank you for being with us. Thank you.
Oh, my pleasure.
Thank you, sir. So we have another question from comments. So the first question, so what is the origin of mass in proton or neutron?
Yeah, so I mean it's a many faceted question. So the mass of the proton or neutron is really coming from several factors. It's coming from the masses of the quarks that make up the proton and neutron, but more so from the dynamics that are happening through the strong interactions. So what happens is, I sort of had a picture on one of my slides a little bit as decoration, but I didn't really talk through it, that as you probe the proton at higher and higher energy scales, what that reveals is more and more details of the dynamical vacuum inside the proton, that you see more and more quark and anti-quark pairs and gluons as you probe the proton at deeper and deeper scales. And so one way of thinking about this is really that the vacuum is not empty. Empty space is not empty. Empty space is a bubbling, boiling, dynamical vacuum of quark and anti-quark pairs and gluons being constantly created and destroyed. And so the mass of the proton comes from the masses of the quarks, but from this dynamical vacuum. So you can understand it all within the theory of quantum chromodynamics. So we've done calculations of the mass of the proton, which comes out of all of the dynamics of this theory.
Thank you, madam. We have another question. So what is quark gluon plasma? Maybe you have already discussed.
Yeah, so quark gluon plasma is a particular state of matter. So you can think of plasma as being another state of matter, much like you have gas and solid and liquid. Plasma is another state of matter, and the quark gluon plasma is a type of plasma state of matter that you can achieve at very high pressure and very high temperature out of quarks and gluons, where you basically don't have protons and neutrons as separate objects anymore, but you have a plasma state.
Thank you, madam. This may be the last question. So, is it possible to replace the effect of gravity as curvature of the space-time with change in mass density of the dark matter? If dark matter is considered as a single entity like a web of spider, it may be a way to unify gravity with other forces.
Yeah, so of course, one of the nice explanations of dark matter would be that it's not actually particles, but that it's a difference in how we understand gravity to what the theory of gravity actually is. And so there's lots of people working on questions of how you might have a different theory of gravity that may replace the need for dark matter. There aren't any convincing explanations right now. Right now, the best explanation we still have is that dark matter is genuinely some type of particle. But of course, that's only to the best of our current understanding. And an explanation of the effects that we see and attribute to dark matter as modified gravity, if there was a nice consistent explanation in that framework, would also be great. So I say this is still how to unify gravity with a stand model and what dark matter is are two of the frontiers of the field. And so our understanding there has to change over coming years and decades.
Thank you, madam. We have another question. So is it possible to observe a free quark?
No, so quarks are confined. That's one of the great predictions of QCD, is that what you have is confinement, that if you try to take quarks far enough apart, then what you have is the generation from the vacuum of another quark-antiquark pair. So if you take them far enough apart, you'll basically have a breaking of that string, and you'll end up with more quarks and antiquarks onto your quark-antiquark pair. So you can never separate them.
Thank you, madam. This may be the last question. So, is there any simulation technique other than Monte Carlo to achieve computational results related to the topic?
Right. So, not in terms of a systematically improvable first principles approach. So, by that I mean what the Monte Carlo technique that we use in lattice field theory gives us is a way of, systematically improving along a trajectory where we know that as you reduce the lattice spacing and increase the lattice volume, the limit will give you back continuum QCD. There are other computational techniques if you make other sorts of approximations or assumptions that you can use. And so there are certainly models that you can use that approximate QCD, and you can study those models computationally. But the only known way to really study QCD in a systematically improvable way is through this Monte Carlo approach. And so depending on your application, you may not need this approach. Maybe one of the others will work for the application. So the answer is sort of a yes and a no.
Thank you, madam, for your wonderful presentation and discussion session. So, sir, would you like to?
I have one question. We know that proton and neutron are composed of d quark and up quark. Except down and up quarks, there are virtual quark-antiquark pair in nucleons. What is the role of these virtual quarks? What are their roles?
So in some sense, saying that the proton is made of up and down quarks is not strictly true. It has the quantum numbers of up and down quarks, but you have quark-antiquark pairs from the vacuum which contribute to every aspect of proton structure, from its mass that we talked about before through to its spin and all of its other properties. So in the momentum decomposition that I showed for the proton, you might have noticed that there was some percentage for the strange quark and some percentage for the charm quark. So those come from these sorts of dynamical fluctuations. So strange quarks, charm quarks, all of the other quarks, they all contribute to the proton's mass, to its spin, to all of the functions, all of the features of the proton.
These are virtual quarks? Are these strange virtual quarks?
Yeah, you can think of them as being the quarks that pop in and out of the vacuum in quark-antiquark pairs.
Oh, yeah. Thank you.
No problem.
Thank you, sir, for making this discussion session more valuable, for joining with us. So thanks, madam, for accepting our invitation. Thanks for giving us time in this corona pandemic situation, though you are too busy with your works. So I'd like to say thanks on the behalf of the Department of Physics, PabnaUniversity of Science and Technology, for accepting our invitation. And I think our students have learned a lot of things about the quarks or to nuclei and about your model and the beyond the particle beyond the standard model. So I think it will help them to fall in love in physics in near future. So thanks again, and hopefully we will arrange another webinar with you in near future. And after the COVID, I will definitely invite you, as you haven't visited our country. So I'll definitely invite you to visit our beautiful country for a short visit and also talk. So thanks again. Bye for today.
My pleasure. Thank you very much.
Yeah. Thanks. And thanks, sir, for joining with us.
Thank you
Bye for
very
today.
much.
Good night.